Okay, good afternoon, everyone. I'm Mariko Owe, research scientist of SoMAS. Thank you for joining the Zoom Taos seminar today. Today's speaker is Kazuomi Morotomi of JRC, Japan Radio Company, JRC. He is presenting research and development of phased array weather radars. First of all, I'd like to introduce him very briefly. Mr. Kazuomi Morotomi graduated Naga University in Japan. He received a master's degree in 2011. Since then, he has worked in the radio company JRC, which is one of the most famous companies developing weather radars in Japan. He has been engaged in developing the phased array radars for more than a decade. When I was a postdoc in Nagoya University, Japan, he was a student of Professor Hiroshi Ueda, who is a same advisor of mine. In Nagoya University, he worked hard for X-band polarimetric radar analysis for mesoscale convective systems. Today, he will present the phased array radar he has developed in the company, and he will present the interesting observations of a storm and tornadoes. During the talk, please leave your message in the chat. If you have questions, please leave your question in the chat. And also, we will have some 10 minutes Q&A time after his talk. Morotomi-san, please start anytime you want.
Okay, thank you, Obe-san. Hello, everyone. I'm Kazuomi Morotomi of Japan Radio Company. I'd like to introduce under the title Research and Development of Phased Array Weather Radar. First, I'd like to introduce myself. I'm a radar engineer. When I was a student, I majored in meteorology. Since joining JRC Japan Radio Company, I have been working mainly on the research and development of weather radar for more than 10 years. In addition, I have certifications in weather forecasting and radio related to my job. This is a follow of this presentation. My presentation is divided into 3 parts. First, let me give you an overview of weather radar. Then an overview of the phased array weather radar is introduced. Finally, I introduce observation results of phased array weather radar. First, about weather radar. Radar is an acronym for radio detection and ranging. This block diagram shows the configuration of the weather radar system. The transmitter generates pulsed signals and amplifies the pulse. The parabolic antenna is adapted as antenna of conventional weather radar. Pulses are transmitted from this antenna, and the receiver amplifies and receives the returned pulse for the target precipitation. Then signal processing is performed on a PC or workstation, and observation data is displayed. This figure is a display example of weather radar observation data. Weather radar rotates the parabolic antenna in the azimuth direction and acquires data for each azimuth and distance. This radar screen shows the radar reflectivity corresponding to the rain intensity. In addition, Doppler velocity in the line of sight direction can also be observed. Next, I will explain the radar reflectivity. Radar reflectivity is a variable that depends on the intensity of precipitation. For example, radar reflectivity of 20 to 50 dBz corresponds to approximately rainfall of 0.5 to 50 millimeters. Generally, color scale of the display uses such a color scheme, and the closer to red, the higher the value. This is an example of using radar reflectivity. By deploying radars all over Japan, it is possible to indicate the rain area. This rain area map can be viewed at any time from the Japan Meteorological Agency (JMA) website. Next, I will explain the Doppler velocity. The velocity of precipitation in the line of sight direction can be obtained from the phase shift for each pulse. Generally, velocity moving away from the radar are represented by positive value, and velocity toward the radar are represented by negative value. Positive values are displayed in warm color, negative values in cool color. In this Doppler velocity map, the lower left is cool color, and the upper right is warm color, indicating that the precipitation area is moving from the southwest to the northeast. Regarding the frequency of weather radar, generally 3 frequency bands are used: 3 GHz, 5 GHz, and 9 GHz bands are called S band, C band, and X band respectively. First, S band radar can observe a very wide range, and the instrument size is large accordingly. The 160 Nextrat radars operated by NOAA in the United States use this S band with an antenna diameter of 28 feet. The instrument of C-band radar system is smaller than S-band, but C-band observation range is a little narrower. In Japan, 46 C-band radars have been deployed by Japan Meteorological Agency (JMA) and Ministry of Land Infrastructure, Transport and Tourism (MLIT). X-band radar has the shortest wavelengths, making it suitable for observation the details of meteorological phenomena. In addition, since the instrument is small, it can be used on an in-peak radar. This map shows the deployment situation of C-band radar by Japan Meteorological Agency (JMA). 20 C-band weather radars are operated by JMA. The remaining 26 are operated by the Ministry of Land Infrastructure, Transport and Tourism (MLIT). In addition, MLIT operates 39 X-band radars, mainly in urban areas. This is about observation mode. Parabolic radar can perform three-dimensional observation by mechanically rotating the antenna in the azimuth and observing multiple elevation angles. For example, it takes about 5 minutes for one volume scan with 15 elevation angles. This is summary of the weather radar. Most of the weather radars currently use parabolic antennas, and one volume scan requires about 5 minutes. There are 3 types of frequencies, S, C, and X, which are selected according to the application. In Japan, 46 C-band and 39 X-band radars are in operation 24 hours and 365 days. Next, I will explain the phased array weather radar. The background of the phased array weather radar development. In recent years, the number of heavy rains has increased. This chart shows the number of annual occurrence of heavy rainfall over 80 millimeters in Japan, while the average number of the first 10 years was 14. The average number of the last 10 years is 24, so an increase of 1.7 times. Heavy rains are caused by developed cumulonimbus. Cumulonimbus develop rapidly in a short time and can reach altitude of 18 kilometers. Therefore, in order to monitor and predict the generation of development of cumulonimbus, it is necessary to observe three-dimensionally and at high speed. In the case of parabolic weather radars, it takes 5 minutes for one volume scan because mechanically scans. Phased array is technology we focused on to reduce this 5 minutes. There has been the technology of phased array for a long time. The main application was for the military to detect flying objects. The picture on the upper left is phased array radar in Alaska. And this white panel attached to the wall around here is phased array. Previously, this phased array system was very expensive because it had many antennas. As the cost of semiconductors has decreased, it has become possible for private companies to develop phased array radar. Phased array weather radar is the application of this phased array technology to weather radar. From here, I will introduce the X-band phased array weather radar developed by our company. The most important feature is that the observation in the elevation direction can be electrically scanned by phased array technology. Therefore, it is possible to observe a three-dimensional space with a radius of 80 kilometers and an altitude of 20 kilometers in 30 seconds when the antenna rotates once in the azimuth direction. Next is a comparison between parabolic and phased array. For example, when observing a three-dimensional space with a radius of 80 kilometers and an altitude of 20 kilometers. With the parabola, the observation time is 300 seconds, and the observation elevation angle is about 15. On the other hand, with the phased array, the observation time is 30 seconds and the observation elevation angle is over 100. Phased array observation enables observation with high spatial and temporal resolution. This above figure is image of transmission and reception of the parabolic antenna type. In the case of parabola, both transmission and reception are observed with narrow pencil beam. Therefore, one rotation is one elevation angle observation. This figure below is transmission reception image of phased array. Transmission electrically scans a wide fan beam by generating multiple narrow pencil beam by signal processing after reception. it is possible to observe more than 100 elevation angles with one rotation. This figure is a comparison of the observed elevation angles. Horizontal axis is distance and vertical axis is altitude. Above figure is a parabolic type. Figure below is phase array type. Comparing like this, we can see the phase array system can perform very dense three-dimensional observations compared to the parabolic system. This video is a comparison of time resolution of radar reflectivity. The left is the radar reflectivity at an altitude of 3 kilometers at 5 minutes interval, and the right is that at 30 seconds interval. You can see more detailed echo movements at right of 30 seconds interval. This video is a comparison of time resolution of cumulonimbus. Left shows the development of cumulonimbus every 5 minutes, and right shows every minute. I think that cumulonimbus condition can be monitored more in real time with the interval of 1 minute. Next, I will explain the phase array antenna. The antenna size is about 2.6 meters by 2.4 meters. Upper part of the antenna is for transmission and lower part is for reception. The transmitting antenna has 16 elements and the receiving antenna has 126 elements. Each antenna consists of long and narrow antenna called waveguide slot antenna, which have slits in the waveguide. By stacking the antennas vertically, electronic scanning in the vertical direction is possible. Therefore, directivity can be changed without moving the antenna. Conceptual diagram illustrates the electronic scanning of phase array antenna transmission. This line is the antenna plane, and 4 antennas are lined up. Each antenna is preceded by phase shifter. First, each antenna has the characteristic of emitting a wide beam in the elevation direction. Here, if all antennas transmit in the same phase, the point at which the crests of waves overlap is in the straight line direction. In other words, the transmitted composite wave propagates directivity in front of the antenna. In the phase from each antenna is adjusted and transmitted as shown in this figure. Composite wave can be propagated diagonally. Therefore, without mechanically moving the antenna, it is possible to transmit radio waves in any direction by electrically adjusting the phase. It's about transmitting fan beams. As shown in blue in this image, the transmission beam is a fan beam that transmits radio waves over a wide range at once. By controlling the phase of each transmit antenna, this transmission fan beam is electrically scanned in the vertical direction, like this. By signal processing after reception, 4 multiple receive beams simultaneously as shown in this image. This is called digital beamforming, DBF. With the above phased array technologies, it is possible to instantaneously observe the range of elevation angles from 0 to 90 degrees. This is equipment configuration of our phased array weather radar. The antenna parts has a waveguide slot antennas on the front and transmitter, receiver, control board, and so on the back. The data received by the antenna is transferred to the workstation, where signal processing and data display are performed in real time. Installation location and observation range. It is installed in Chiba, east of Tokyo, and since 2015 has been observing an area with a radius of 80 kilometers and an altitude of 20 kilometers at 30-second intervals. The upper photo shows the radar installed on the roof of the laboratory. The lower photo shows the inside of the radome. Light map shows the observation range of the phased array weather radar, which is installed in the position where it can be observed urban areas and major airports. By arranging multiple antennas and controlling the phase of each antenna, the observation direction can be electrically changed at high speed. As a result, the observation time required for one volume scan has been reduced from 300 seconds to 30 seconds compared to the parabolic system, and the elevation angles has been increased. Next, I will introduce the observation results by phased array weather radar from next slide. This movie is a three-dimensional movie of radar reflectivity. You can see the convection of the cumulonimbus cloud and the falling precipitation clouds. If you look around the red circle, you can see the precipitation occurred at an altitude of about 4 kilometers from 2030, like this, and fell to the ground. Convection like a fountain can be confirmed in the upper part of the cumulonimbus cloud from 30 o'clock near the blue circle. In this way, phased array weather radar observations have high temporal and spatial resolution, so cumulonimbus clouds can be observed three-dimensionally in real time. Next, the gust front generated by falling precipitation core seen near the red circle is shown. I describe the gust front. The gust front is an outflow boundary at the tip of a strong cold downdraft from developed cumulonimbus. Wind gusts can occur near the gust front. This is a video of radar reflectivity at 400-meter height. There is the cumulonimbus seen in the three-dimensional movie. After the precipitation core falls, we can see a bow-shaped echo moving eastward on the east side of the cumulonimbus. This is consistent with the gust front generated by divergence of downdraft. This movie is vertical cross-section of cumulonimbus that generated the gust front. Vertical axis is distance altitude and horizontal axis is distance from the radar. Upper figure is the radar reflectivity and lower figure is the Doppler velocity. Looking at above figure, you can see how the precipitation core that occurred at the 4-kilometer heights falls. Looking at the Doppler velocity in the lower height became stronger after the fall of the precipitation core, like this. Early observation of falling of this precipitation core is useful for predicting the gust front and downburst. In this video, left side is photograph of a cumulonimbus, and right side is radar reflectivity of phase array weather radar, viewed from the same viewpoint. It is an interesting example because we can observe fine unevenness of the cumulonimbus and the shape of the upper anvil in 3 dimensions. From the next slide, I will introduce the tornado observation case in 2019. I'd like to introduce observational results of typhoon-induced tornado observed by our phased array weather radar. A tornado occurred in Chiba at 8:08 on October 12, 2019. Estimated wind speed was 65 meters per second and there were 10 casualties. This video shows the damaged area. Trees were knocked down and buildings and cars were badly damaged. I will introduce a paper that summarizes the results of detailed analysis using phase array weather radar data. This figure shows the positional relationship between the tornado damaged area and the phase array weather radar. The tornado that occurred was very close, within 5 kilometers of the phase array weather radar, so we were able to obtain detailed observation data. Next, details of the damaged area are shown enclosed in full frame. The damaged area from the southeast to northwest, and the total length was more than 2 kilometers. The red circle are the area where the building was particularly damaged. This is weather chart at the time of tornado. When the tornado occurred, the typhoon was located about 500 kilometers south of the tornado, and its central pressure was 945 hectopascal. According to the JMA radar echo, the tornado was generated by cumulonimbus within the outer band northeast of the typhoon. Enlarging the blue frame in the phased array weather radar observation area in the right figure, this is radar reflectivity of phased array weather radar at 100 meters height. This echo moving in the northwest direction is the parent cloud that generated the tornado. At the edge of this parent cloud, there is a tornadic echo. A tornado generated at the center of this tornadic echo. This is time series of 100 meters height, radar reflectivity, and Doppler velocity. Dashed rectangle indicates damaged area by tornado. you can see tornadic echo passed over through the damaged area.
Hey, Dina. No.
I will show you more detailed behaviors on each time domain. Firstly, 8 minutes before the tornado. These figures show observation data at 100 meters, 1000 meters, 2000 meters, and 3000 meters. At 8 o'clock, at the south tip of the parent cloud, hook echo and bounded weak echo region and mesocycle are seen. All of them are characteristics of radar observation for supercell. On the other hand, ecotop of the parent cloud was about 9 kilometers, which was lower than ecotop of classic supercell. Therefore, this parent cloud is mini supercell. There are images 4 minutes before the tornado occurred. At the tip of the parent cloud hook echo, a smaller hook echo appears. This smaller hook echo suggests the occurrence of mice cyclone. This is time series of 100 meters height with the reflectivity at the time of tornado occurrence. Enlarging the tornadic echo reveals the lower mesocyclone inside the middle mesocyclone. And at the center of tornadic echo, there is a maximum value of radar reflectivity, like this. This maximum indicates debris ball caused by tornado debris. The next slide shows a vertical cross-section along this line. Upper figure is radar reflectivity and lower figure is Doppler velocity. The figure on right is enlarged view of the dashed line in the figure on left. Looking at radar reflectivity, we can see both structures suggest the existence of strong updraft. Looking at Doppler velocity, we can see that the mesocyclone in middle height and mesocyclone in lower height form a three-dimensional vortex structure. This is the structure of parent cloud. The parent cloud is a mini supercell with three-dimensional vortex structures of mesocyclone, and tornado. In addition, debris ball was observed at low altitude. Finally, I will introduce the evolution of debris ball. This figure is time series of the vertical cross-section of the debris ball. The dashed line indicates the ecotop height of the debris ball. Debris ball exists 1 minute before tornado. When a tornado occurs, the ecotop rapidly develops up to 550 meters. 30 seconds after the occurrence, the maximum radar reflectivity reached 54 dBz and the ecotop altitude dropped to 450 meters. At 8:09, the ecotop increased again. This is a consideration of evolution of debris ball. It was a forest area from 1 minute before outbreak. 30 seconds after that, it was an area with a lot of building damage. The echo top of the debris ball is dropped and radar reflectivity is maximum for this event. This suggests that the main component of the debris changed from light natural debris to heavy building debris. This is the first case where the detailed evolution of debris ball caused by tornado associated with typhoon has been analyzed. Summary, we have developed an expand phased array weather radar. It takes only 30 seconds to finish for a three-dimensional volume scan within a radius of 80 kilometers and height of 20 kilometers with high spatial resolution. Succeeded in observing typhoon-induced tornado in detail. The cumulonimbus that caused the tornado was a mini supercell. A three-dimensional vortex structure was formed inside the parent cloud. We were able to observe the evolution of debris ball generated by tornado debris due to changes in land cover. From the above, the tornado was observed in detail by the phased array weather radar, which can observe the three-dimensional space instantaneously. Therefore, it may lead to improved accuracy of tornado monitoring and prediction. Thank you for your attention.
Thank you very much, Morotomi-san. Thank you for the interesting and nice presentation. Well, let's move on to the question time. Please your reaction. Please raise your hand reaction if you have questions. Minhua, go ahead.
Yes, so I have a simple question. Is this radar you described commercially available, or it's just a research radar?
I think that's the question. Morotomi-san, can you answer this question?
聞こえたんですけど、ちょっとわからない。
コマーシャルに販売しているのか、リサーチレーダーと。
Can people
research
buy
only.
a radar like this from your company?
This expand is research only.
Research, okay.
Yeah, I had the same question. Yeah, thank you. Edmond?
Hi, thanks for a really great presentation. You can only get details like what you got if the radar is within really close range of the weather system. So is this a mobile radar, or is it just has to be sort of fixed location?
This is not mobile.
Okay.
Because very heavy.
I have following question. Are you planning to move this radar to another locations, or are you your company is planning to fix the same location for a while?
Same location.
Okay.
I think there's a question on the chat.
Okay. Yeah, I see there's some question from Muhammad. Muhammad, you wanna ask a question directly? Okay, I can talk here. Morotomi-san, can you see the question in the chat? Thank you for the amazing presentation regarding phase array radars. Why you do not use more than one phase array to cover the 360-degree horizontally rather than use one rotate mechanically?
Oh. すみません、もう一回お願いしますか。
2つ以上のレーダーを使ったりしますか？もっとカバーを広げるために。
研究用なので一つしかないです。
He mentioned that he planned to only one radar. This is for the developed for the only research radar only. But I think this is a good idea. Morotomi-san, I have following question. Do you plan to develop more than one radar in your company?
Next development of no X-band, C-band, multi-parameter phase array weather radar we developing now.
Okay, that's good.
If I can interrupt,
Brian?
this is
Oh,
Malcolm
sorry.
Bowman. The reason why you cannot have one that looks 360 degrees is because the antenna itself is a square plate, is a flat plate, and the elements of, as the speaker showed us, sends out a beam, and you change the phase by you change the phase electronically, so it's like tilting a mirror. But you couldn't have a mirror looking in all directions at once. That's why it has to mechanically rotate. But I have a question about how much power is put out by these radars, and does it affect commercial air flight radar?
Malcolm, your question is basically
how much?
You are thinking to
How much power? How much power?
Okay.
Power is 1.6 kilowatt.
1.6
transmitter?
And presume it does not affect commercial aircraft radar.
Oh, good question. Morotomi-san, Malcolm's question is, you are transmitting the X-band with a little bit high power, possibly high power. Is there any effect on the aircraft radars? In the Tokyo metropolitan area, there are a lot of aircraft flying.
Yes.
There's any contamination or influence?
すみません、日本語で、
X バンドレーダーと、飛行機のレーダーと、
はい。羽田と成田がたくさんあるので、飛行機はたくさん通っていて、ノイズとして捉えられていますけど、効率点除去で、除去しています。
He mentioned that this radar detected the airplanes several times because there are the huge airport in this area. But these echoes can be removed by the noise, no meteorological echoes. But I think there is no affection in the radars between them. They have similar frequencies, but a little bit different frequencies, and then it's not big issues. Before installing this radar, this location, there are several assessments how much the power need and the frequency, the radar beam, whether the radar beam affects the airport radars or not. So
yeah, it's also interesting that 5 gigahertz is the same frequency band that home Wi-Fi uses.
Ah,
Maybe some houses that are close to the radar could be affected.
yeah, yeah. This is my experiment. When I had some radar measurement in the different location in Japan, there's some, yeah, problem that the radar was affected by, it was 10 gigahertz radar. The radar was affected by some cell phone noises. But it's not big issues.
Thank you.
Brian, you have a question?
Yeah, no, this was a very interesting talk because I've been trying to learn more about these radars since the radar group here with Pavlos has one of these in some form. Yeah. We're trying to use this radar, actually phased array for winter storms. The issue with winter storms is that the reflectivities are much lower than your cumulonimbus example. At least as you get up toward the top part of the cloud, they get close to zero. And I noticed that your bottom scale was 16 dB, and we've had similar sensitivity issues. So I'm just wondering, is there a way technically or somehow to make this radar more sensitive, to be sensitive down toward more 0 dB to get more cloud top activity?
Yeah, I have the same question to Morotomi-san. Morotomi-san, can you answer this question?
すいません、日本語でお願いできますか。
図で見せていたのは 16dB とか 20dB 以上ですけど、もう少し小さい dBz まで見えますか？センシティビティはどれぐらいですか？
難しいかな。この図で 5dBz のと地面表示をしています。なので
This is
5dBz。
5dBz threshold of the cloud.
Okay.
What is the sensitivity of this radar? Morotomi-san. Minimum, what is the minimum detectable reflectivity?
レーダーに近ければ 5dBz ぐらいから見えます。
Oh, he said it's from 5dBz. 5dBz is a minimum detectable
Well, that's
reflectivity.
actually better, and Mariko, you might know more than me. I think that's better than what ours is currently calibrated for, which is around that 10 to 15. So maybe there's a way to work to understand to get ours down to 5. I don't know but that's why I'm wondering if there's a flat baseline of 15, or if it can get down to 5, that would be great.
Yeah, 5 dB would be great. It's a precipitation in the ice precipitation regions. Yeah.
So Brian, how much power does your portable unit put out?
Well, yeah, actually, I don't, Mariko, I'm not sure if we have how our unit compares to the one the speaker has.
Sorry, I don't remember exactly the power, but we have several different techniques. Low power transmission, but we transmit long range and then compress the B and the pulse to get better sensitivity. And also we can do the short pulse transmission to get the
Higher power.
Short pulse is a more high resolution, but less sensitivity. Wow.
It's interesting. Many years ago, I was involved in anti-submarine warfare in the ocean. We were using phased acoustic transmitters to get a very directed beam, trying to get reflections off Soviet submarines.
Yeah, interesting. Is there any questions? Yeah, Muhammad gave one more question. Morotomi-san, do you think about the advantage of forecast beam? Forecast beam, I am not familiar with a forecast beam. Muhammad, what is a forecast beam? I guess that his question is the difference between the fan beam and the narrow beam. Morotomi-san, can you explain a little bit more about the fan beam and small beam, narrow beam?
送信の時は、広くファンビームで観測して受信後に分割するというイメージですか？そういうことですか？
He gave one more foreign question. By steering or curvature array. Curvature array means Muhammad, can you explain what is a curvature array? Sorry. Steering or curvature array. Sorry, I can't understand your question. I'm sorry. But I have a following question here. You used the fan beam, which is a little bit wider in the vertical. I am wondering if there is artificial echoes catched by the wide beam. For example, ground craters and other stuff. Do you have any problems in getting ground craters by this wide range beam, wide beam? Ground crater 除去はどうしてますか？
グランドクラッター除去は MTI オンリーです。
Sorry?
MTI だけですね。
What is MTI?
Moving Target Indicator。速度幅で、切ってます。
You just remove the ground crater when the Doppler velocity is equal to 0. Is that correct?
Yes.
Okay. Well, it's almost time. Is there any questions? Okay. Morotomi-san, thank you for the great presentation, and I loved these nice images, nice animations. Actually, I love the 3D cloud images. Thank you for giving your presentation from far away from here, which is behind of the earth from Japan. Thank you very much.
Thank you very much. ありがとうございました。